Okay. Now let us let us now learn how to start and set up the process. Okay, so this is not right or wrong. I'm just going to share my way of doing things. Okay, I normally run my simulated annealing in 2 steps. In step 1, I find the correct start temperature. So I first start with my function. Look at the rough value there, whatever. I substitute, I get some, I randomly generate a solution, substitute and get my, uh, this is my objective. And I try with a small proposed change and get the value and find my delta E. Now, this is my rough delta E. So based on that, I determine my T value. So as I showed you, ideally, this delta E should be 5 to 10% of T for the initial probability to be 95, 90%. So I ensure that my delta is selected as 95% or 90% of my T. So now that I know delta E, I fix my temperature like that. But I'll take one order of magnitude high, one order of magnitude low also. So if my T based on this calculation should be 10, I try with 1 and 100. So what I do is I set up my simulated annealing where the algorithm pseudocode is create a random solution. Now find its, sorry, create a neighbor, accept the neighbor if it makes the objective better. So my function, depending on maxima or minima, is going to be, if it's maxima, I will use this. If it's minima, I will use this. So that I'll always get the probability for a worst solution. We discussed this in one of the previous videos. You can check it. So if it gets better, accept it. If it gets worse, accept it with this probability. Okay. Neighbor. Now I cool the temperature with a geometric factor. Now, so create a random solution and try it 3 experiments with 3 temperatures. Let's call it initialize temp 1. Okay, which is 1 or 10 or 100. Create a random solution. Neighbor. Accept or reject. Now, new temperature is equal to 0.95 times the old temperature. Cool it. And again, now I remember whatever is the solution, my neighbor solution or original which I retained. Okay, either accepted the neighbor or accepted with a probability, which means rejected also. So based on that. Now, for whatever I have there, solution, create a neighbor. Again, accept or reject and reduce the temperature. Again, accept or reject. Like that, I do some 50 or 100 iterations. Now I initialize T2 and do 50 or 100 iterations. Then T3, 50 or 100 iterations. Now I plot how the X value, the solution has varied, or objective has varied, either of them. Okay. I want the solution ideally to vary like this if I'm maximizing or if I'm minimizing. I want it to jump a lot. Okay, I will be scared if it's like this, which means it's not trying out various options. Okay, you should look at either the delta E, RE, depending on of the chosen solution, what is the objective, or even the X value. This is a bit tricky if there are multiple dimensions in the solutions, right? X1, X2, X3, plotting becomes difficult. So normally I plot the E value, the objective function versus iterations. So I'll get three curves. Let's say one curve behaved like this. Um, one curve behaved like this. And another curve again behaved like this. I prefer the one that explored the space more efficiently, right? So that is my step one. Now let's say T2 has one. Now I do the final analysis where I fix the temperature at T2. Now I start with, at that temperature, I ask it to do 20 or 50 iterations. Okay, now create a random solution. Then neighbor, accept or reject the neighbor using the probability. Okay, and continue. And now I continue for this many iterations at the same temperature. Okay, 20 iterations. Then I cool the temperature. T new is equal to 0.95 times T old. And I also reduce the iterations by the same factors. I new is equal to 0.95 times I old. Of course, I'll only take integer if I get a fraction. So at 950, I will then do only 19 iterations. Then the next temperature, I will only do 18 iterations. Like that, I reduce because my understanding is at high temperature, there is a probability of acceptance. As I bring down the temperature, the probability of accepting a bad solution has anyway gone down. So I just do one or two iterations at very low temperatures because only the better solutions are accepted. So at higher temperature, on the other hand, you can think of it as I am exploring multiple local minima at higher temperature, fixing on one where things are behaving well. And as I come down, I'm more or less transforming into a regular greedy or hill climbing search where I'm only accepting better and better solutions. So I try fewer iterations at low temperatures. So and then always, plot the behavior of objective function. So it should go and you should see where do you stop. One way to stop is say, hey, you know what, do 2000 total iterations. If the behavior at the end of that is like this, you can stop because you're not seeing much of an improvement and it sort of stabilize the objective. Okay. On the other hand, if it is still growing like this, you may want to increase the 2000 to 5000 and try it. Okay. And if it's behaving like this, it is not stabilizing. So you need to, change the temperature or cooling rate. Most likely you're accepting bad solutions. So your temperature and energy are such that even at lower temperatures, you are accepting every solution there is. So change the value, increase that, reduce the temperature to a order of magnitude, final temperature, and figure out. So you have to freeze the solution at some point. Okay. So there are multiple parameters that you have to set. One is the start temperature. Okay. The other one is cooling rate, linear or geometric. The third one is end criteria. Okay. After 1000 or after 2000 through observation. What else? And the objective function itself you have to set. It's either the function or you have to sometimes cleverly create some functions. And how do you generate a random neighbor? Random solution you have to be able to generate, and neighbor also you have to be able to generate, such that the space is explored nicely. You shouldn't be searching only a small region, you should be searching all over the place. So you should think about the business problem at hand and define all these things. Once you define all these things, the algorithm is very simple. Set a temperature, set a cooling rate, set a end criteria, create a random solution, check for the objective, and create a neighbor, check for the compute the objective. If neighbor makes the objective better, accept it. If it makes it worse, accept with a probability that is based on how worse it is and the temperature. And then do multiple iterations at that temperature and fix on one solution, then cool it to the lower level, and then repeat the entire exercise.